The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
A very happy morning to all my dear students. After a long gap, I think the classes is going to start again. And so today's class, I just want to share a small thought with you by a famous renowned personality, Bill Gates. And what he says is, don't compare yourself with others. Don't compare yourself with others. And if you do so, you are insulting yourself. Yes, that's very true, children, because every person in this world is unique. Do you agree with me? We all are unique, and if we compare ourselves with anybody around us, we are selling ourselves. We are actually selling ourselves, and we try to mold our personality or change our personality to satisfy somebody which is against our grain, that is, which is against our wish. So we are not supposed to do that, and we need not try to impress others. Let us be what we are. Forget about whoever thinks about you. You just have to be yourself. Believe in yourself and do not compare, because if you compare with others or if you compete with others, we try to change ourselves. We are not natural. We are not what we are. So with this, I want to begin the class today. And I know all my children are unique and you have your own strength and weakness. So let us let us cross all the weakness and let us focus on our strength, build our strength to become a very good individual. Okay, so with this, the class for today is with a continuation of D and F block elements, where we are focusing on the oxidation states. We have already learnt that D block elements show variable oxidation state, right? Variable means they have a large number of oxidation state, because most of the metals we know they possess positive oxidation state by losing electrons. They try to lose electrons and become a cation. And we know transition elements are metals, and we know metals always lose electrons to gain a positive oxidation state. So these transition elements, they show variable oxidation state. If you see the first series of transition elements, right from scandium till zinc, scandium do not show variable oxidation state. What is the atomic number of scandium? It is 21, right, which is nothing but 3d1 4s2. So it can lose these 2 electrons and maximum it can show only +2 oxidation state. So it does not have the participation of D and S just like the other elements in the transition series. So scandium is the element which do not show any variable oxidation state. And if you see right from scandium, titanium, vanadium, all this chromium, manganese, iron till zinc, the middle of the series, that is, if I start from scandium until zinc, the middle of the series, right, the 5th and 6th element, they will be showing the greater number of oxidation state. Example, like manganese, which is having an atomic number of 25, shows n number of oxidation state. That is, it shows +2, +3, +4, +5, +6 and plus 7. So these are the different oxidation states shown by manganese, which comes in the middle series of the transition series. And if you see, the lesser oxidation state will be present at the extreme end. Say right from scandium to zinc, scandium will be showing very few oxidation state, and we said of course no variable oxidation state. Zinc of course will show plus 2 oxidation state because it is also having zinc atomic number is 30. So it will be 3d10 and 4s2. So the d orbitals are completely filled. So it cannot lose its electron. So it will be lost only from the s subshell. So that's why zinc loses 2 electrons to become Zn plus 2. So that the reason is because either few electrons will be there. See, if I have only very few electrons, I can lose only that electrons. So I have only 1 electron in my d subshell, or I have only 2 electron in my d subshell. I can lose only those electrons to become plus 2 or plus 1 oxidation state. The next reason is too many d electrons. In case of zinc, 3d10. So it is completely filled. So there are no unpaired electrons or no electrons from the d orbitals to get lost. So what happens? The reason is because there will be only few electrons in the d orbitals or too many electrons, that is the d orbitals being completely filled. So these are the reason for the transition elements to show lesser oxidation state. And if you see the reason, it has come in even in 10th standard you have learnt. Why the d elements they show variable oxidation state? If you see p block and s block, only s subshell take part in the chemical reaction, or if you see p block element, only p subshell take part in the chemical reaction. But when we come in the case of d block elements, both the d and the s, that is the penultimate d subshell and the outermost s subshell take part in the chemical reaction, then the oxidation state differ by unity, which means if I say for manganese it is plus 2, then there it is plus 3, then I have plus 4, plus 5, plus 6. The difference between each oxidation state is unity, only 1. So that is why the reason that it shows different oxidation state. So I can say there is a participation of the penultimate d subshell and the outermost s subshell by the d block elements, which is the primary reason for those elements to exhibit different oxidation state. And if you see the low oxidation state elements of the transition elements, they have a tendency to form complex compounds. What are complex compounds? That is, they can take up the groups from the other solutions and they form a compound which is called as a complex compound. If you see nickel tetracarbonyl, CO means carbonyl. Here it is iron pentacarbonyl. In both the cases, the oxidation state of nickel and iron is 0. So these are some of the reasons why the transition elements exhibit different oxidation states, even they exhibit null oxidation state, that is 0. Now we will be just going through the oxidation state tendency for the formation of plus 2, plus 3, plus 3, plus 2 and plus 1 by the d block elements. We shall see the trends that takes place in the d block elements with the oxidation state of M2 plus or as a metal, or with M3 plus and M2 plus. If you see in the textbook, they have given a column with the element losing 2 electrons and what will be the electrode potential value. Across the table, if you see, copper is having a unique behavior. Every other element, transition element, has got a negative E value, except with copper, which is having a positive value, is just because the inability to liberate the hydrogen from the acids. Children, if you can recollect, in 10th standard we have studied about the reactivity series, arrangement of elements in the decreasing order of their reactivity, right from potassium till gold, if you remember children. In that, hydrogen will be placed as a reference element, that is, those metals which are placed above hydrogen can displace hydrogen, or I can say can liberate hydrogen from the acids. and the elements which are placed below hydrogen, we have copper, silver, gold. These three elements can never displace hydrogen or can never liberate hydrogen from the acids. So if in that case copper has got a tendency that it cannot liberate the hydrogen from the acid, that is inability of copper to liberate hydrogen gas from the acids. So that is the reason that it has got a positive E value. And if you see the other elements which all can displace hydrogen will be having a less negative value across this series is just because they are increase in sum of the first and second ionization energy. What is the first ionization energy? Removing electron from the outermost shell. Once I remove electron, the number of electrons in the outermost shell has decreased. Now what will be the second ionization energy? Removing again the second electron from the same atom. So the sum of the first and second ionization energy will be more, which is the reason for the value of the electrode potential of these metals to be less negative. So that is the trend with M2 plus oxidation state. And if you see with M3 plus and M2 plus, for scandium if you see 3d1 and 4s2, if all the 3 electrons are lost, it will have a noble gas configuration. And we know when an element exhibits a noble gas configuration, it cannot react, or I will say it is an inert element. It becomes inactive, chemically inactive. Zinc, a high value for zinc is because it has got an atomic number of 30 with 3d10 and 4s2. So if these 2 electrons are lost from the 4s subshell, it will be having a d10 completely filled configuration, which is again responsible for the high value for zinc. And next one again, if I take iron, iron has got 26, right? So it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. If it becomes Fe3 plus, losing 3 electrons, 2 electrons from S subshell and 1 electron from D, so it will become 3d5, and we know whenever it is 3d5, a partly filled, or I will say half filled or completely filled subshells are more stable. So my D5 configuration becomes more stable. So that is the reason for the value for iron. So these are the general trend in the oxidation state. Now we will learn about stability with higher oxidation state. Stability of higher oxidation state, what does it mean? When I take a transition element, how far it can react with other elements and become stable. That is, when a transition element reacts with a third element outside the transition series, how far the stability will be there. So if you see the fluorides and oxides, that is the fluorine and oxygen has got the highest to stabilize. They have the more stability property when they react with the transition element. That is just because of the higher lattice energy. In fact, we have learned about lattice energy, children. That is, lattice is the rock salt structure where you have to break the bond like sodium chloride to become Na plus and Cl minus. Similarly, this fluorine has got a higher lattice energy once it forms a compound and high bond enthalpy. Enthalpy we know again energy to dissociate or to break the bond. So both are very high in case of fluorine. But what happens when you compare it with oxygen? Oxygen has got the more stabilizing power when compared to fluorine when it reacts with manganese. Say you have MnF4, a tetrahedral compound. The same thing when it combines with oxygen, it forms Mn2O7. That is 2 manganese sharing 7 oxygen atoms, where it forms a MnO-Mn bridge, right? Surrounded by 4 oxygen atoms around. So this is just because of the capacity of oxygen being more electronegative, or I would say compared to fluorine being less electronegative, it could easily stabilize with manganese. If I see the chemical reactivity, we already know that transition elements are chemically reactive, but copper, when you compare to other elements being having a positive
E value will be little less reactive than the other elements. All the metals are more reactive. The electrode potential E value, which is showing the decreasing in the divalent cations, that is tendency of the transition elements to become a 2+, losing 2 electrons, will be decreasing. That is, they have a tendency to decrease in the divalent cation, or it is just because of the increase in the ionization energy of the first and the second electron with respect to a transition metal. And moreover, when I say chemical reactivity, we have already learned that the partly filled, that is the half filled and the completely filled d orbitals are more stable. So when it becomes d5 after losing electrons, or when it becomes d10, they become chemically inactive, that is they become inert, stable, they do not react in any chemical reactions. So these are as of with the oxidation state. Now we will be learning about the magnetic properties, catalytic properties, colored compounds. With that we can stop the class for today.
Now we will see about the magnetic property of the D block elements. Magnetic properties are basically, we have studied, it can be paramagnetic, it can be diamagnetic, and it can be ferromagnetic. When I say diamagnetic, it has got completely filled electrons, and diamagnetic substances are repelled by the magnetic field. Paramagnetic substances are attracted because of the presence of few unpaired electrons in the orbitals. And we know ferromagnetic is just a powerful magnet which can easily get attracted. That is, I can say the extreme form of paramagnetism is ferromagnetic character. Now these unpaired electrons, when I say orbital is having an unpaired electron, this unpaired electron will be possessing a magnetic character, which we call it as magnetic moment. Now that magnetic moment is a reason for two simple things. First one is spin angular momentum and orbital angular momentum. When I say spin angular momentum, the electron spinning around its own axis, and orbital angular momentum, electron spinning around the orbits, that is around the nucleus. So spin angular momentum, an electron spinning on its own axis, orbital angular momentum in different fixed orbits. So these reasons cause the magnetic moment of the unpaired electron, which is the reason for the magnetic property of the D block element, or I can say a particular metal. So how to calculate whether the given metal is paramagnetic or it has a magnetic character? By using a spin 1 formula, spin only formula, which is mu is equal to square root of n into n plus 2, where mu is the magnetic momentum, n is the number of unpaired electrons. So with this formula, we can find out the magnetic moment, that is the mu, and thus can determine the magnetic character. The unit for magnetic moment will be in Bohr magneton, which is written in simple way Bm. With 1 unpaired electrons, if 1 is an unpaired electron, 1 plus 2, it is 3, square root of 3 becomes 1.73 Bm. And what happens? The magnetic moment will increase whenever there is an increase in the unpaired electrons. So if number of unpaired electron increases, the magnetic moment also increases. So there is a question which definitely comes, they will be just giving you the atomic number and the element. You will have to find out the number of unpaired electrons, substitute the value for n here, and then find out the value for mu. So this is how we do with the magnetic property. Now we shall learn about our colored ions catalytic property. Formation of colored ions. See, an electron from d orbital, lower d orbital, will be jumping into a higher d orbital. So it needs to gain some energy when it has to jump from a lower energy level to a higher energy level. In such case, the energy will be depending on the frequency of the light that is absorbed. It will absorb some light with a certain frequency,
and that frequency will be lying in the visible region. When I say visible region, it is nothing but VIBGYOR, that is violet, indigo, blue, green, yellow, orange and red. So that color corresponds to the complementary color of the light absorbed by the electron when it jumps from the lower energy level to the higher energy level. And that frequency of the light will be indicated or will be depending on the nature of the ligand. What is ligand? For that understanding, we will be studying about complex compounds or complex formation. So I would say transition elements, they form colored compounds. We know copper sulfate, blue in color, manganese dioxide, black in color, cobalt nitrate, pink in color. So we have even seen in our lab different color nature of the transition compounds. Now what is a ligand? To understand about ligands, it is nothing but metal ions has got a tendency to bind with anions or neutral molecules. So why does it have a tendency? It is just because of three simple reasons. It has got a very small size of metal ion. The size of metal ion is very small, but it has got a high ionic charge and it has got lot of d electrons available in the d subshell. So the d orbitals available for the bond formation, high ionic charges and the small size of the metal ion are responsible for the transition metal to bind with anion or the neutral molecules. So here my iron is a metal, transition metal. So what is this Cn minus? It can be an anion, it can be a neutral molecule, but here it is an anion. Neutral molecules, I can take water or ammonia. Say copper combines with water, H2O5. Here this is my neutral molecule, okay, this is my anion. So this is called as a ligand. That is, we put a square bracket, inside we write a metal ion, inside that in a parenthesis, in a bracket we put some anions or neutral molecules. So these are called as ligands. So I said here ligands are responsible for determining the frequency of the light. So those are the ligands, and these are responsible for the formation of the complex compounds. The next important property of D block element is the formation of or the having a property of being a catalyst. We know catalyst alters the rate of reaction, that is, it reacts with the reactant molecules, forms the complexes and it does not change in its chemical composition. Once the reaction is over, you can regain your catalyst in the same way how much you have poured in. So catalyst can be positive and negative. A catalyst can increase the rate of reaction and it can also decrease the rate of reaction. Why does a transition metal show a catalytic property? We know it has a tendency of forming multiple oxidation state. Role of a catalyst is to make the reaction alter, change. So it should have a tendency to form multiple oxidation state, also form temporary complexes which are called as transition complexes. So these transition metals form the complexes. Example, you have vanadium in contact process, finely divided iron in Haber's process. So role of a catalyst we have learned also in the chapter surface chemistry. What is the role, how does it react, how does it form a temporary complex and how does it come back after forming the product. With this, we have only two more things, formation of interstitial compounds and alloy formation. We have come to the last part of the today's session, formation of interstitial compounds. This word interstitial we have learnt even in the first chapter. Interstitial site means something that is vacant sites. We have some empty spaces in a complex or in a compound, where in those spaces some of the anions or cations get trapped. So here small atoms like hydrogen, carbon and nitrogen are trapped inside the crystal lattice of metals. So when I say titanium, vanadium, chromium, manganese are metal compounds, in that metal lattice there will be some empty spaces where these small atoms get themselves trapped. So they form compounds like TiC with carbon, Fe3H with hydrogen. And those metals, they show non-stoichiometry. We have also learnt about non-stoichiometry in the first chapter, and these are neither ionic or covalent, and they have very high melting point, very hard. They continue to show their metallic conductivity even after forming the interstitial compounds, and they are chemically inert, which means once they form an interstitial compound, they do not react at all. And the last one is an alloy formation, which we already know what is an alloy, combination of metals over other metals. So here it is a homogeneous solid solution of atoms of one metal, which you distribute randomly over the atoms of another metal. Why this happens is because of metals having similar radii, and they are very hard, very high melting point. Best examples are ferrous alloys, which has got a wide application with varieties of steel, and also transition metal with a non-transition metal forming alloys, which are like brass, bronze, which has got a wide application as an industrial importance. So with this, we are stopping the class for today. If it's possible, I'll include some videos, or else I'll be posting the video as such. So you can also browse through, children. If you have any doubt, do let me know. Okay, thank you, children.